Okay, so today's lesson is going to be on graphing data. And some of this will be review, some of this will be some new material. So anything that is old and you've heard it before, please feel free to fast forward, but take a minute and you're going to have to pause at some points because I'm going to ask you to do some graphing on your note sheet. So let's take a look at this graph. We have a graph of mass on our y-axis and volume on our x-axis. And if I were looking at this, notice also too that there's a multiplier here. So all of these values are multiplied by 10 to the minus 2, and then the unit comes after that, grams. And then likewise, the volume has a multiplier of times 10 to the minus 3, which isn't relevant for drawing our best fit, but is relevant for finding our slope. And also notice that there's vertical error bars. So this is your uncertainty in all of these masses. Okay, so that is your range. That's your plus or minus on your masses. There's not any, there's no horizontal error bars. Okay, generally speaking, we will only talk about vertical error bars, but doesn't mean it can't happen. And so we're going to do a couple things. We're going to first draw a best fit. Okay, nothing new there. But because there's error bars, we're also having to draw a min and max best fit. Okay, so let's first take a look at what it looks like if so go ahead, pause it for a second and draw your best fit. Okay, knowing that you want to not necessarily hit all of the data points, but you want to make a nice spread of the data. So you want to kind of have some above the line, some below the line, the nicest spread. And this is up to you. No two people are going to draw the exact same best fit. So when I drew my best fit, I have a line that looks like this. Okay, so a couple things to note. Notice that the line does go pretty much through the origin. We have a very, very small y-intercept. And also that some of them are below, like this line right here, this point right there. Some of them are above, and some are kind of far away. Okay, but then some kind of go right through. Now, to draw my minimum best fit, okay, that's going to be the one that has the least amount of slope. It is the bottom, excuse me, this will be the greatest slope. It's going to be the bottom of that error bar connected with the top of that error bar. And then our maximum is going to be that error bar. Let me use a different color here. That point right there connected with that point. So go ahead, pause the video for a moment and draw that best fit. And what you should get is something that looks something like this. Okay, now what I want to do is find the slope of all three of those lines. Okay, so I'm going to do one at a time. I'm going to draw first the slope, or calculate first the slope of my best fit. So what I'm doing is I'm following along this line and I'm looking for points. Okay, that looks pretty, well, let's see if we can find another one. Okay, there's a point right there. Okay, notice that it goes through the grid of the graph paper. And then there's another point right there that goes through the grid of the graph paper. And what I'm going to do to find my slope is draw a little box. Okay, typically I do dotted lines, doesn't matter what you do. And this is going to be my delta M, and this is going to be my delta V. Okay, so now notice that on the y-axis, that goes from 1.5 to 2, and there's one box in between. So every box is a quarter of this multiplier, so a quarter of a hundredth of a gram. Okay, so if I go 1, 2, 3, 4, 5, 5 quarters is 1.25. And if 2, so from 8 to 6 is 2, and there's 5 bars, I'm going to do 2 divided by 5, and that's going to be 0.4. Okay, so every box represents 0.4 times 10 to the minus 3 cubic centimeters. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that would be 4.4 times 10 to the minus 3 cubic centimeters. And likewise, this would be times 10 to the minus 2 grams. So to do my slope, I'm going to do that number divided by that number. Okay, now I'm going to repeat that same process for my max and min line. Okay, so I'm going to repeat it for my green line right here. Okay, find two spots that go through the grid of the graph paper and do delta y over delta x or delta m over delta v. And then repeat that for the red line. Okay, so once again, pause the video, find your slope of all three, and then we'll kind of compare answers. So first of all, what type of relationship? Okay, notice that we have a line, so we're dealing with a linear relationship. But because it also passes through the origin, we can also say that this is a direct relationship. So something that is linear and direct is not only a line, but also goes through the origin. Now, your numbers may be slightly different. No two people are going to draw the same best fit. But I got numbers of 3.125 grams per cubic centimeter for my best fit. My minimum slope was 2.19 grams per cubic centimeter. And my maximum slope was 3.75 grams per cubic centimeter. Okay, so if I want to find my uncertainty in my slope, okay, excuse me, my random error in my slope, I'm going to do max minus min divided by 2. So that is 3.75 minus 2.19 divided by 2, and that gives me a value of 0.78. And what I'm going to do is round it to 1 sig fig, so I have 0.8, and that is grams per cubic centimeter. So my final answer, my slope, plus or minus my delta slope, is going to be equal to 3.125 plus or minus 0.8 grams per cubic centimeter. Okay, and we'd have to know how many sig figs we had in both the y and x-axis, the mass and volume axis, to be able to round this. But you can leave that like that for right now. So let's ask ourselves, what does our slope, what is the physical significance of our slope? So sometimes the quantity itself helps you answer this, sometimes the units. Okay, so we have a mass on this axis, which is in grams, and we have a volume in cubic centimeters on our x-axis. So we ask yourself, what does mass over volume equal? And if you recall from chemistry and the last video lesson, that equals your density. Okay, once again, the Greek letter rho. Okay, kind of looks like a funny P, but yeah, the physical meaning of our slope is the density of whatever material, okay, or the letter rho. So the general equation of a line is y equals mx plus b, so we have that. But translate to our specific situation, okay, we never want to leave in our lab book that the equation of our graph is y equals mx plus b. You have to ask yourself, what's on the y-axis? What's on the x-axis? What's our slope? What's our y-intercept? So in this case, our y-intercept was 0, so that's going to cancel out. Okay, so we have mass on our y-axis equals our slope, which ours was 3.125 plus or minus 0.8 grams per cubic centimeter, times volume. Now, here's the beauty of this. You can tell me any volume, okay, let's just make it easy, 1 cubic centimeter, and then I could tell you what my mass is with the error bars, the random error. So that is if we have a linear case. What about if it's nonlinear? At this graph, I try to draw a best fit I'm not really going to be able to hit many of the points just by drawing a line. A better fit for this graph is going to be looking something like that, okay, a bit of a curve, okay, and maybe you could do a better job on your paper than what I have here. So if I have y, just some generic y on my y-axis and x on my x-axis, and here's my data from my lab, the question becomes, what is this relationship? Okay, so ask yourself, what did you call this in math class? Okay, so you might have called it a squared graph, okay, but odds are you called it something like quadratic, okay? And this states that y is proportional to, so that symbol means is read as proportional to, x squared, okay? So if we want to make this a graph also called linearize, okay, we're going to talk a lot more about this linearization. I take the same y values, so repeat those, and I'm going to plot it versus x squared. So I'm going to square all of my data. So I'm going to ask myself, what is 4 squared, 5 squared, 6 squared? Okay, so you should be able to do these, okay, relatively easily. So we have 4 squared is 16, 5 squared is 25, 6 squared is 36, okay, 7 squared is 49, 8 squared is 64, and then we had 10 squared, which is 100. And so I'm going to replot these. I'm going to take the same y values and now rescale it going up to 100 on my x-axis. So pause the video for a moment and rescale it and see what the results yield. So I did this on my paper and I got something that looked like that, okay? A linear relationship, okay? And it's not exactly direct, okay? There is a bit of a y-axis, y-intercept that I didn't really show here. So what is the meaning of the slope? Well, without units and what these y and x's values, okay, we're not really sure. So I'm just going to put an NA as not applicable for right now. But what is the equation of the line? Well, I got a slope of about 3. So my slope is about 3. So I have y equals mx plus b. Okay, and like I said, we're going to just ignore the y-intercept for right now. So y equals mx. So I have y on my y-axis. I have a slope of 3 for m. And then, but what do you have on your x? Okay, it's no longer just x by itself. It's actually x squared. So my mathematical relationship, my equation, is going to be y equals 3x squared. Okay, so don't think just by squaring your x values that you're going from a nonlinear case to a linear case and then you could just leave it as x. You've got to make sure that you include that squared term because that's what you physically did to the graph. So what are some other graphs that we can look at? Okay, so we already talked about one of them, something that is linear and direct. Okay, so this is linear and direct. If we have a graph that looks like this is linear, but not direct, so this is not direct. Okay, we might be able to see a line that looks like this. Okay, so it is a line, despite it not looking that straight. This is not what we call an inverse. Okay, this is actually what's referred to as an indirect line. Okay, inverse and indirect are two different relationships, and I know you've probably used those words interchangeably in the past. What else? Well, we can see a quadratic like we saw in case 2. Okay, it's your parabola, and so you can call this a quadratic, or maybe you want to call it a squared. Okay, either one. We can have a square root. And then lastly, we can have an inverse graph. So an inverse graph is your hyperbola, okay? Or this actually can be inverse squared. We'll talk about this in greater detail the difference between these two. And actually, without any numbers, you can't tell. But so right now, either inverse or inverse squared. Okay, we know it's one of the two. Okay, and inverse means as one goes up, the other one goes down by the same proportion. Okay, and like I said, we'll talk more about this in lab. So those are the graphs that we'll see this year. We'll speak about each one in greater detail, how to linearize each nonlinear one. And that's all for now. Thanks for listening. Have a great night. We'll see you tomorrow.